Hello everyone. I hope I'm audible. So can anyone confirm that I'm audible or not? Thank you. So welcome everyone in the tutorial sessions of Advanced Linear Algebra NPTEL course. So I am Milan Kumar Mal, a PhD scholar in the Department of Mathematics, IIT Madras. So in this tutorial sessions, basically these tutorial sessions will be each Saturday from 6 p.m. to 8 p.m. Till end of the course. Okay. So in these tutorial sessions, basically I will discuss um, in these tutorial sessions. Basically, I will discuss some problems which will help you to solve assignments because you have to solve submit assignment in each week. So so basically what I will do, I will in this, for example, in this tutorial session, this current tutorial session, in today's tutorial sessions, I will discuss some problems which will help you to solve assignment 1. So let's start with some problem. So I will not discuss any theory, not much, unless it is required, and I will discuss some problems and whatever the required theorem needed at that time, I will discuss. And also, throughout these tutorial sessions, if you have any specific problem regarding this course, you can ask me in these tutorial sessions. Also, you can mail me to the mail ID. This is the mail ID. You can mail me ma21d018 at the rate of smail.iitm.ac.in. This is my email ID. If you want, you can, if you have any problem, you can mail me. I will address those problems in the next tutorial sessions. And also you can ask here, I will try to solve those problems here. If that problem is not in upcoming assignment, then I'll completely solve that problem. Otherwise, uh, eh, otherwise I will, if that problem is in the assignment, then I will try to give you a hint which will be enough to solve the problem. Okay, so let's start with the problem. Okay, so this is 24th. So unless if you have any problem, if you have any questions regarding the material, or if you are not able to understand anything, you can open your mic and ask me. I'll try to explain. And unless other is required, it's better to not to. It's better to always turn off your video camera, basically. So let's just a minute. So so this is the first problem. What it says: let A be a matrix. Uh, this is the matrix what is given: 1 2 3 minus 1 4, and 2 4 6 minus 2 8, and these are the rows basically, and x is an tuple like this and y is an tuple like this. So now what is the question says, that the system Ax equals to has solution if whatever the required, whatever the condition it is given, we have to choose the correct options. So to solve, what to do, first of all, we need to this type of problem, to solve this type of problem. So what is, suppose we are giving, so here I will discuss some little bit about the theorem of this which is required to this problem basically. So whenever let A be m by n matrices over a field that can be complex or real. So here it is not mentioned, so that doesn't affect anything. Let A be a matrix, m by n matrix, and suppose x is equals to x1 to x, this will be n, and y is equals to y1, y2, yn. This will be m. Yeah, this will be m. This is m. This is m by n times 1. This will be m by 1. Yeah, this is the transpose. So this is suppose we are giving let ax is equals to y. So how to solve that problem? That first questions, and second question is that whether there exists a solution or not. First main problem is that whether there exists a solution or not. So if there is a solution, how to solve this problem? So these are the things one can generally try to understand, and those things will completely help you to solve this type of problem, and any problem this type of problem. These are very easy thing, not much. They are actually related to the system of linear equations, but I will not go that till that unless it is required. So what it says, so you are giving that x equals to y, something like that. So when there exists a system of when there exists a solution, basically. Okay, so um, so here if you know that there is something called row reduction process. What is row reduction process? So let me write that. What is row reduction process? Row reduction process. This is elementary row reduction process. Elementary row reduction, basically one can write instead of row reduction process, elementary row operations basically. What are the elementary row operations? What are the elementary row operations? Those things are already discussed in class, I mean the lecture video which is uploaded in NPTEL portal, but here I will just quickly discuss. Suppose you have a matrix, and there is three basic elementary row operations. First is that you can multiply, one can multiply a non-zero constant to any row. Okay, this is the first elementary row operation, and second elementary row operation is that you can multiply. Suppose you are having a matrix like this A. You can multiply. Suppose let R is not equals to S, and R and S are less than equals to M. That means they are integer. Let RS and R comma S are integers. Let R comma S are distinct positive integer, and so that and R and S are less than equals to M. So that will denote the row R and row S, basically something like that. So what you can do, you can replace. One can replace. Another elementary row operation is one can replace rth row of A by row R plus some constant C row S, where C is a constant coming from the field. That means that can be either real number or complex number. Okay. Now the third thing, so this is basically what is said that suppose if I just say, I will give an example. So suppose you have another third option. Third option, what it says that those things I will discuss and with this problem also. Third one is that you can interchange two rows. One can interchange two row of A. So if you do any of the process of this, any one or two or three or any multiple times also, any of this process with the matrix A, then after that if the matrix changes to the matrix another matrix R, which is called something reduced in some sense, then still they will have still there will not be any problem to finding the solutions. So but I will not do that. So basically here what is saying that when there exists solution, this is what I want to mean, the system X has solution. So whenever you have this matrix A x equals to B, let us write A dash is equals to A with Y. So what is this? This is equals to basically, I'll write the exact form. This is what equals to 1 2 5 minus 1 4 2 4 6 minus 2 8, 1 1 1 0 2 3 6 9 minus 3 12. This is, and here I will write y1 y2 y3 y4. Now we will do the row reduction process with this matrix. Okay, and after that, number of non-zero row in this portion. So now the system will have the solution if, so let us write, so let, after row reduction, if A dash becomes R y dash, something like that, then the system Ax is equals to y will have solution if and only if number of non-zero rows is equals to number of non-zero rows in R is equals to number of non-zero rows in R mod y. Okay, y dash basically. So actually this problem can be solved very easily. We don't need to do all these things. So it seems that what to do all this way, we don't need to do all these things. Okay. So but this problem can be solved. How to? So let me first do that. How it is easy to solve basically. If you look at carefully, this first row is actually uh, first row is actually that if you carefully look at that, row 2 is actually 2 times row 1. Okay, and row 3 is actually 3 times row 1. So whatever the y, so suppose you have system, whatever the, what, and this system means something like that. This system will be like x1 plus 2x2 plus 3x3 minus x4 plus 4x5 is equals to y1. This is the first equation. Second equation is that 2x1 plus 4x2 plus 6x3 minus 2x4 plus 8x5 is equals to 8x5 is equals to y2. This is the second equation. Third equation is that x1 plus x2 plus x3 plus x2x5 2x5 is equals to y3. And third equation, fourth equation is that 3x1 plus 6x2 plus 9x3 plus minus 3x4 plus 12x5 is equals to y4. These are the four equations. So if you look at carefully, as I have said, first equation, second equation is actually 2 times first equation. So therefore, from here, what we can say that 2y1 has to be equals to y2. Okay, and third equation is actually the 3 times of the first equation. So from there, from these two portion, one can say, so let me write this one. From these two portion, one can say that R3 has to be equals to 2. This is what happened. R3 is equals to. Therefore, from here one can say that Y4 has to be not R3. This is R4. Yeah, Y4 has to be 3 of Y1. So if you solve Y1 from these two, what you'll get? You will get Y2 by 2 is equals to Y3 by Y4 by 3. So that you will get 3y2 is equals to 2y4. So then in that way, what it will be, 3y2 is equals to 2y4. This is the correct option. But this way you can get. But what I am trying to do, that is general solution. You can get easily this way. Solution is clearly visible. Okay, but this is not always you will get that much easy, that much lucky that this row will be clearly linear combination. I mean, fourth row is linear combination of first row. Second row is actually the direct linear combination of the first row. So this way you can get. But here is the standard process. Whenever you have the I mean direct solution, you can get like the easily. If you can solve the problem by observations, then you don't need to do the whole process. But if you are not able to solve the problem by observations, then it's better to go all the way using the full steps basically, but you can do quickly. So now if you do the row operation, so the same row operation you have to do here. So what you will get, you have to do 3 4 operations. That first you have to do that r2 dash is equals to r2 minus r1, 2 times r1. R3 dash is equals to r3 minus um, r1, and r4 dash is equals to r4 minus 3r1. If you do all this step, so what you'll get, first row will be as it is, y1. Second row will be, if you subtract it, it will be 0 always. So this will be y2 minus 2y1. And third row will be, um, if you subtracted 0 minus 1 minus 4, 1 2 minus 2, and here will be y3 minus y1, and that will be 0 0 0 0 0, and y4 minus 3 y1. So this is what you'll get. But note that this is the r, this is the r, and this is the y dash. Okay, now what are the number of non-zero rows in r? There is two non-zero row, 1 and 2, right? So but if you want to get the same number of non-zero row with r, so number of non-zero row in R is actually 2. Okay, and if you want to get, if one wants to get same number of non-zero row in R mod y dash, something like this full thing is, I'm saying R mod y dash, then we should have y2 minus 2y1, that has to be 0, and y4 minus 3y1, that has to be 0. So this combinedly will give that 2. So basically here will get y1 is equals to y2 by 2, and y1 is equals to y4 by 3, and combined you will get that 3y2 is equals to 2y4. Same problem. So answer is B. That's correct answer. But you can do in both way, using the full general process and without using general process, just by observing the matrix. Okay, by observing the matrix you can also solve, but it's, if you are not able to solve by just observing the matrix, then it's better to go all the step by step process. Okay, so now let's concentrate on the another problem. So 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 here is also some more facts which is not required for this particular problem. Here I have said that after row reduction, if you know the row reduction process, then after row reduction, a dash means a by a, this matrix becomes r mod y dash. So this system will have solution if number of non-zero row in r is equals to number of non-zero in r mod y. But now suppose they are not equal, number of non-zero row and number of non-zero row in both sides are not equal, that means system is inconsistent, system does not have any solution. Now another thing is that suppose you have the same number of non-zero row in both r and r mod y dash. Now then what you can say, that there is this solution. But what is the number of solution? One can have more solution. I mean, solution can be single solution, solution can be multiple solution, solution can be infinite number of solution is also possible. Okay, unique solution is possible. Finite number of solution, whether possible or not, finite number of solution is actually not possible, and infinite number of solution is the possibility. So there is two choice, either it will be unique solution or infinite number of solution, but that depends some other facts. Whether if this is equals to exactly equals to 4, then we will have unique solution. If it is less than 4, then we will have infinite number of solution. Okay, so this is general thing, which is maybe for right now you don't need that much. You can do just by looking at the problem. Let me do this. So here is another problem. So what it says, let V be the set of pairs AB belongs to R square and F be the field of real numbers. Let the addition and scalar multiplication be defined as this way. then which of the following statement is correct? Okay, so okay, the first problem what I have discussed, is that clear to everyone? If there is any doubt, you can ask. There is no same to asking the if there is any doubt. Okay, if there is any doubt, you can still ask. You can ask anytime. I am assuming that that is clear to everyone. So now this is the second problem. So let V be the set of pairs AB belongs to R2 and F be the field of real numbers. So basically F is actually R. Okay. Let the addition and scalar multiplication be defined as this way. Then which of the following statement is incorrect? Question is incorrect. Okay, not correct. What are the things here asked? The closure property with respect to the addition holds for V, and the associative property with respect to the addition holds for V. Additive inverse does not exist. Additive identity exists. I believe these terms are known to most of them, but still I will discuss a little bit. What is mean by the closure property of addition? So basically here what is giving V be a set and which is equipped with two binary operations, and they are addition and scalar multiplication. So what is the addition? So this is in general denoted by this plus, and at scalar multiplication in general denoted by dot. This is what it is. So scalar multiplication. What is scalar multiplication and what is addition? Addition means you are taking two element like x and y, two element from V, and you are defining x plus y. You are defining. This is not always generally something addition. I mean, when you are writing 2 plus 3, that's 5, that's separate thing. But this is just defining the addition property, that x plus y. You can suppose you are not giving numbers, then how to add those things? Okay, so then addition means addition of something. Okay, that so suppose you are giving two function, then you have to add, so that means they are not number, you have to add something new function, that one can say. So addition can be something different. Suppose this can be defined like this way, x y minus 2. This can be x and y to real number. We are defining addition something like this, not addition, this symbol, this is symbol. Okay, something like that. This is also possible, but whether that is doing any help or not, that's separate thing. Okay, now okay, so here addition means, suppose here the terms is that here addition is given by this way. Okay, so suppose you are having two element, so here is the addition. Note that usual addition, if you just expect, so suppose you have two element AB, two pair basically, and A1 B1 in R2. Okay, V be a pair AB. Okay, V be the set of pairs AB. Okay, these are the V actually this V actually this. Okay, so now defining addition like this way, like A comma B. What is the usual addition one should get? Usual addition, anyone will say that this is the addition, right? But here it is not. Here it is defining like this way. The first term will be as it is, second term will be 0. So that means this is not universal addition like we already did that usual number addition or something. That's not like that. Here is addition something defined. Unless it is defined, you can't say anything. So this is the addition and scalar multiplication. So when you are doing addition, this addition means of two elements in V, and scalar multiplication means you have to take any element from the field, which is actually a real number here. Field is single if it is given, and you have to multiply that. This is the scalar multiplication with an arbitrary element AB coming from the V, that is defined as CA0. This is what it is. Usually scalar multiplication means, suppose you have pair 2, 3, you want to multiply 5, so you will consider this 10 to 15, but this is not what it is mean here. Okay, so this is something different. So now the question is, here it is asking, this is the addition mean basically. So now the question is, first thing, the closure property with respect to addition holds for V. Closure property means if you take two element AB and A1 B1 belongs to V, and this way addition the resulting element, that element is also in V or not. This is what it is mean the closure property. Okay. And similarly, closure with respect to scalar multiplication means after multiplying scalar, whatever we are getting, whether that is closed or not, that is inside the set or not. Closure can be failed. For example, suppose you have a rational number, okay, and but suppose you have real number, okay. This is V and this is field, okay. So now you want to multiply F element C from V F and another element X from V. You want to multiply Cx, whether this is in V or not. Always this is not always, because for example, if you take x is equals to 1 and c is actually some irrational number root 2, that's again real number, but root 2 dot 1, that is not in the V, where V is, oh sorry, so I have to interchange basically. Yeah, V is equals to Q, and yeah, V is equals to Q, and F is equals to R, okay, real number. So in that case, if you take C belongs to V, that's some irrational number root 2, and X belongs to V, that is actually Q root 2, that is not in V is actually Q, because root 2 is not rational number. So always this multiplication is not always closed, okay. So that depends whether this is closed or not. This closedness means this closedness means that element after addition or multiplication, whether that element again in the main set V or not. This is what it is closeness. So here it is clear that this element a plus a1 comma 0, this element is in the set R2, pair of elements of real numbers. So that's why this is true. But here it is asked which is incorrect. Okay. So this is true. So that can't be the correct option for this problem. Now the second thing is that associativity property. What is the associativity property? CATVT property. But associative property of addition, yeah, associative property of addition means that if you take three element a1 comma b1, a2 comma b2, and another element a3 comma b3, this is suppose three element you are taking from the set V basically. Okay, so you are taking from the set V. Associativity means that a1 comma b1 plus a2 comma b2 plus a3 comma b3, this is whether same with a1 comma b1 plus a2 comma b2 plus a3 comma b3, whether this is. So this is what it is mean. First add these two term and then add this term, and here it is first add these two term and then add a1 comma b1. So this is what it is, and here associativity will hold, but don't think this associativity will always hold. Okay, associativity also can fail. Okay, so one can give some example like real rational. In that way also one can give an example that where the rationality fails, but here it will be, because let's see the left hand side what it is says a1 plus a2 comma 0. This is what it is by definition, and a3 comma b3, again it will be a1 plus a2 plus a3 comma 0. Okay, and what is the right hand side? A1 comma b1, it is as it is, plus this term will be a2 plus a3 comma 0. So this will be a1 plus a2 plus a3 comma 0. So associativity also holds. Associativity holds means this is also true. Now the second question is that additive inverse does not exist. What is additive inverse? Additive inverse means additive inverse. Additive inverse means for any element AB belongs to V, additive inverse is something like CD, another element in V, such is some CD belongs to VD such that A comma B plus C comma D is actually the zero element. Okay, that should be the zero element. And what is the zero element here? Zero element here is actually 0 is an zero element, but 0 is an zero element. So 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 whether always there exists or such element exist or not, additive inverse exist or not, this is what it is. So you can know that that will always exist. Suppose you have AB, you just add minus a comma 0. Still this is also additive inverse. Additive inverse in this case can be more than 1, but not always, because there something will fail. So this is by property a minus a comma 0. So this is equals to 0 comma 0. So additive inverse exists. Okay, so additive inverse is also exist. So that means the last term, last option will be the correct. uh, Sorry, does not exist. No, additive inverse. Sorry. Here is the some mistake I have made. Additive inverse. So additive inverse means this should hold, but there should first exist something. Okay, so here is some additive inverse. So here is some mistake I have made. Sorry. This is what it is. The problem will hold. So first, to have additive inverse, what we should have additive identity. So first, let's see what is additive identity. Additive identity. Additive identity is a unique element like CD belongs to V such that for any AB belongs to V, A comma B plus C comma D should be again A comma B and is equals to C comma D plus A comma B. But by the property of addition, this is means A plus C comma 0 and this is means C plus A comma 0, and which is same with A plus C comma 0. So now the question is that if these two is equals to again A comma B, what we should have? We should have that C is equals to 0 and B can be any number, because B there is no, B has to be 0. Okay, B also has to be 0, but that's not, because we have to do for any AB belongs to B, we should be B, but B need not be 0, but B need not be 0, because what we have said, additive identity is a unique element CD belongs to V such that for any AB belongs to V, um, any element AB belongs to V, we should have this property should hold. But here it is forcing, if this property holds, it is forcing that B has to be 0, but B need not be 0. One can take AB which is B, where B is not equal to 0, for example 2, 3, this is in V, because V is actually R2, right? So that is there, B is not 0. So that means there does not exist such element. So that is there does not exist such CD in V. So that imply additive identity does not exist. Additive identity does not exist. And when additive identity will not exist, there will not be no additive inverse. So additive identity exists, this is wrong. And when additive identity does not exist, additive inverse will not exist. That implies that when, and this is natural, it is universal basically. So this is universal. When additive identity does not exist, then there is no additive inverse. Then there is no additive inverse. This is standard group theory. Whenever you have a group, uh, and if you don't have identity of that group, you will not have the inverse. Okay, so if you want to have inverse, you have to first find the identity or not. This is what I made the mistake. Okay, so this is the second problem. So if you have any doubt in this problem, any regarding any um, definition or anything, maybe I made mistake, you can point out as well. Okay. Also, if you have any doubt, you can ask anytime. Okay. I don't know. Okay, let me. This is another problem. I hope it is visible. Okay. Okay. Let A be a matrix. This is the matrix given 0, 0, 0, minus 1 something. The row reduced form of matrix A is. So what is the row reduced form first? That I have discussed little bit but not completed there. So let me write what is row reduced form. What we have said, there is three elementary row operation. One is you can multiply a non-zero scalar with any row of a matrix. This is the first elementary row operation. Second is that you can take a row and you can add another row by multiplying another scalar. Okay. And the third elementary row operation is that you can interchange two rows. So this is the three elementary row operations. So now you can perform elementary row operation with a matrix. But until, I mean, till when you should do the elementary row operation, after which you can do, you can say that okay, this is enough. And first of all, what is the elementary row operation helps us? Suppose you have a matrix, okay, there is many element is there, and if you do elementary row operation, that makes many elements to zero. So if you have a matrix with maximum number of zeros, so then that matrix is easy to handle, easy to do some calculations. But if you have much more numbers which are not zero, then that matrix is not that much easy to handle. So to make calculations easy, we do the elementary row operations. But row reduction process is something, row reduced form is something, if you perform the elementary row operations, so after some time you will get a matrix which is something like enough zero is there. Okay. After that it will not help much. This is element row reduction process. I mean row reduced form. And row reduced echelon form is something that you have to arrange that row reduced matrix, which is also helps further to solve something. Okay. So row reduced form. So what I have said, you have a matrix, you can do the three type of elementary row operation, but until when you can do, until you get the row reduced form. So what is the row reduced form of a matrix? So what I've said, that suppose you are giving a matrix something like this, and you have started to do the row reduction process, but until when you will stop there, until when you get the row reduced form. And and what is the row reduced form? So let's see what is the row reduced form. First of all, um, each non-zero entry of a row, first non-zero entry of a row, non-zero entry of a row is 1. That is called leading term, called leading entry. Okay, this is the first thing. Second thing is that, so that means suppose you have started first row, you are looking at the first row. First row can be, all of them can be zero. Okay, if all of them are zero, you don't need to do anything. If there is a non-zero term, you have to hit the first non-zero term. If the first non-zero term is 1, then you don't have to do anything. If the first non-zero term is not 1, you have to multiply something so that row, such that first non-zero terms become 1. For example, in this case, suppose this is the first row. For example, this 24150. This is actually last row, but for example, I am assuming this was in the first place. So the first non-zero entry is 2. Okay. So first non-zero entry is 2, but that's not 1. So how to make that 1? You have to multiply half with the full row. So then that will be 1. Okay. Second thing is that, and that term is, after, if you get 1, that is called leading term. If a column has leading term of some row, that is 1, leading term of some row, then all other terms in that column should be 0. I think this toward the row reduction process. Okay, this is the called row reduced form. If a matrix, if you do row reduction process, and if you are reached to this point, then that is called the row reduced form. I hope there is no more steps. Still can clarify that. Row reduced from, I'm not able to find. Okay, I think this is all. This is called row reduced form. This is all. These two are the call. So that means suppose for example this one you want to do the row reduction process. I want to obtain the row reduction process. The first non-zero entry of the first row, that's -1, but I want to get 1. So how to do? What will do? I will do from this matrix to this. So okay, let me write that matrix again. So because there will not be enough place. Okay, still you can do here. So from here to here. So what we'll do? Multiply -1 with R1 and replace that. R1 dash is equals to -1 R1. So this will be 0, 0, 0, 0, 1. Because first non-zero term of the of this first row is -1, but I want that has to be 1. Okay, so that what how one get multiplying -1. And the other term is 1, 2, 0, 3, 0, 1, 2, -1, -1, 0, 2, 4, 1, 5, 0. Now, second, let's do, and second term, what is that? If a column has leading term, that means this the fourth column has leading term, then of some row, then all other terms in that column should be 0. Here, all other term in the fourth column is 0, so there is nothing to do. Now let's come to the second row. Second row, first leading term is 1. Okay, but but the other two terms in the below of 1, they are not 1, not 0. So we want to make that 0. So how to make that 0? So that is what we will be doing here. 0, 0, 0, 0, 1. Let's keep this row as it is. So how to make the third row term, I mean this 1, 0. How to make that? We can do, because we are allowed only to do the three types of row operation: multiplication by scalar, and interchange of rows, and you can add or subtract to row. Okay, this is what it is one can do. So now what will do? R3 dash is equals to R3 minus R1. And similarly, if I want to delete 2 here, so what we have to do? R4 dash is equals to R4 minus 2 R1. Okay, so now 0, 1. So now what you will have? This is what it is. So if you subtract row 1, row 2 from, this is row 2, sorry, not row 1, row 2 from row 3, then what will have? 0, 0, -1, -1, -3, 4, 0. And here it will be, you have to multiply 2 to the second row and subtract it, that will be 0, 0, 1, -1, 0. This is what it is. So now look at that. So here is the leading term of the second row, and all other entry in that column where 1 exists is 0. Now the next process is that, just a minute. Next process is that, let's go to the third row. Here is the leading term is -1. Okay, but we have to make it 1. So how to do? -1. So basically R3 dash is equals to -1 with R3. So what we'll get? This is all terms will be as it is. Only the 0, 0, 1, 4, 0, 0, 0, 1, -1, 0. This is what it will get. So now here is the leading term, but the term just below that is not 0. So we want to make that 0, and because all other above term are 0, so that's why we want to make that 0. So you want to make 1, 0. Okay. So how to do that? So how to do that? That we have to do that R4 dash is equals to R4 minus R3. Then we'll get. So 0, 0, 0, 0, 1, 1, 2, 0, 0, 0, 3, 0, 0, 0, 1, 4, 0, 0, 0. If you subtract it, then you'll get 0 here, -1, -5 here, 0 here. But this is what I got. I think I made a mistake. Just a minute. Okay, -5. But now let's go to this. Here is the leading term, okay, of the third row, and all other entry on that column is 0. But now let's go to the fourth row. Fourth row, the leading term is minus 5, but I want uh, that has to be 1. Okay, so how one will get? One can multiply minus 5. So okay, let me check with that 0 0 1. This is what it is matching. 1 2 0 3. This is first one is matching. Second one is not matching. So this is what it is matching. You can look at. So I'll directly. I think this is what it is matching. 0 0 1 1 2 0 3 0 0 0 1 4 0. Yeah, this is what it is matching. So I will get R5 R4 dashed is equals to minus 1 by 5 into R4. So you'll get this one. So this is the correct option. So these are the row reduction process. Okay. I hope it's clear. If there is any doubt, you can ask. Anytime you can ask regarding even the previous doubt also. Yeah. Okay. So this is another problem. So what it says, let us giving that you have a matrix A, then the matrix B such that A and B are row equivalent. Okay, what is row equivalent? So first see what is row equivalent, and after that we'll look at things. Row equivalent. Let A be a m by n matrix. So once again, you can do only the 3 type of row operations. Okay, you can't only the row operations. Sometimes it happens that people are doing row operations in between do column operations. Then you'll complete that will be a complete messed up. Answer will be incorrect. Even answer is correct, you will not get any marks in any place. Okay, and I believe answer will be always correct, incorrect, because column there is nothing like column operations. Only the row operations. You can add row, you can subtract row, you can multiply with some row, you can interchange row. These are the only things, row operations. And also one can do column operation, but that's separate thing. That's not much. One can say that not much acceptable way. But when you are doing column operation, you can only allowed to do the column operation. There is no row. You can add to column, you can multiply something with column, you can interchange two column. That's only row column mix up should not be happen. Okay. So A, B, and M by N matrix. If B is obtained from A, then by elementary row operations, by some finite number of elementary row operations, number of elementary row operations, then B is called row equivalent to A. So why this row equivalent things actually, or some equivalent things is called? Because suppose you have a matrix A, suppose Ax is equals to 0, you have some solution of this system. This means this is a system of linear equation, right? X1, X2, Xn is the inter variable and A is the matrix, something like that. You can A and here is multiply X1, X2, X3, X4. This is equals to 0, 0, 0. This is what one can think, but that is one can write Ax equals to 0. Now, if you are getting the matrix B, which is after row operations from A, suppose you get the matrix B, then you will have Bx is equals to 0. This system, solution of this system is same with the solution of this system, exactly same. Okay, if x is something such that Bx equals to 0, then that x will satisfy Ax equals to 0. And if x is something that Ax equals to 0, that x will satisfy Bx equals to 0. So that's why, so whenever you have row equivalents, so this system will have the same set of solution. So basically what it means, that x belongs to, suppose we are in m by n, so this will be in Rn or Fn such that Ax is equals to 0. This is same with x belongs to Fn such that Bx is equals to 0. One can say that in that case, whenever row equivalence, only in that case. Okay. So row equivalence means you will get a matrix on the row reduction process. If you are getting a matrix on the path of the row reduction of a matrix, then that will be row equivalent to the previous matrix. So basically, so how to get that row equivalent matrix? So let's start with this matrix. This is the matrix we are giving. Okay. So as we have said that we can do the row reduction process, and in row reduction process one of the step is that you can interchange row. Why I am saying the interchange row? Because sometimes happens that first entry is not 1 in this matrix. The first row is given 3 minus 6 2 minus 1. The leading non-zero term is 3, that is not 1, but that's not actually problem. You can multiply that first row by 1 by 3, but the problem is that if you multiply 1 by 3, this element will become 2 by 3, this 2 will become 2 by 3, minus 1 will become minus 1 by 3. Okay, I hope this matrix entries are not much small that you can't see. If you are not able to see matrix entries, should say, then I'll try to increase the volume so that you'll get the see. You can see. Okay. Okay. So thing is that it's not a good idea to multiply 1 by 3 with the first row, because that will make enter some fractions, and whenever you have fractions, then it will be difficult to do some calculations. But we are allowed to do something which is called interchange of row. So let's do that. Let's take the um, final row, because the final row first entry is 1. Okay, so that will be something like good start. So to have a good start, let's interchange the first row to the final row, fourth row to the first position, and shift all other row to down. Okay, so what will happen? So what will happen? You have to do that R1 dash is equals to R4, R uh, R2 dash is equals to R1, R3 dash is equals to R um, R2 dash is equals to R1, R3 dash is equals to R2, and this is all. No, sorry, R4 dash is equals to R3. So that means interchange. I'm not doing much rocket science. This is just interchanging. I mean, shifting all other row downwards and taking last row to the first place, because we will have the ready-made one in the first place. So you get the one. Okay. So now what is the next step? Next step is that we have to make all other entry in this column 0. You can look at the last entry 0. So we have to make 3 and minus 2 0. So how to make that? You can do that R2 dash is equals to R2 minus 3R1, then you will get 0, and R2 dash is equals to, R3 dash is equals to R3 plus 2R1, you will get 0. So first row will be as it is. So we are subtracting row 1 3 times from the row 2. So 0, it will be 0, 3 times is minus 1, 3 times that is minus 1 already. Okay, and adding the first row 2 times to the third row. So this will be 0, this will be 0, this will be 3, and this will be 3 again, and 0 0 0 1 1. So you can look at that, makes very easiest things, because that makes most of the term 0. So now the first non-zero term of the second row is minus 1, so we have to make 1 it is. So let's do that. Minus 2 1 0 0 0 1 1 0 0 3 3 0 0 1 1. Yeah. So now what we have done, that R2 dash is equals to minus 1 by minus 1 into R1, minus 1 times R1. This is, R2. This is what we have done. Next step is that this is the leading term. We have to make this is 0, this is 0, this is 0. Okay, let's do that. So to make this one 0, what we have to do? We have to subtract row 2 from row 1. So row 1 dashed is equals to row 1 minus row 2. So this will be 1 minus 2 because here is 0 all. Okay. So this is 0 and this is minus 1. 0, 0, 1, 1. And we want to make this is 0. How to do? That row 3 dashed is equals to row 3 minus 2 row 1. 3 row 1. Okay. So 0, 0, this will be 0, 0. And another is that row 4 dashed is equals to row 4 minus row 2. Okay, this is again 0, 0, 0. So this is the row reduction form. Now you don't have anything to do because row reduced form is there because first non-zero entry of the first row is 1, all other entry in that column is 0. Second row has the leading term 1, all other entry in that column is 0. And third row has no non-zero term, fourth row has no non-zero term. So this is the row reduced form. So what is matching with this? I think this is matching with the final one. I think, yeah, this is the final answer. And it will not match any other. Okay, so this is the answer. I hope it's clear. Again, if you have any doubt, you can ask. I will repeat. Now, here is a interesting term that A equals to B. Here is the thing. So now what we are saying the row reduction process. Okay. So actually what is happening when we do the row reduction? Suppose you have a matrix A. Suppose you have a matrix A. And when you are do row reduction, actually you are multiplying some. This is the suppose m by n matrix. Okay. Suppose A is an m by n matrix. When you are do row reduction process, that's actually nothing but multiplying A from the left hand side and m by m matrix, invertible matrix, which is called the elementary matrix. There is three type of elementary row operation. Corresponding to that three type of elementary row operations, there is actually three type of elementary uh, matrices. There is only three type of elementary matrices. You can repeatedly multiply those matrices. You will again get the elementary matrices. What are that? When you are doing, suppose A is an m by n matrix in that situation. When you are doing scalar multiply with the rth row, so that means in that case, elementary matrix is something like scalar multiplying by C at the place of R, for example. CR, multiplying C at the place of Earth. I don't know what it is called symbolically. I don't remember actually. So that's what it is. You have all identity matrix, only the Rth row will be C. All other entry will be as it is. Okay. So Rth row will be Rth row diagonal will be C. All other entry is 0, 0, 0, 0, and like all other entries like as it is. Okay. So this is the elementary matrix. When you are when you are interchanging, or suppose you are doing something like that, row I plus C row j, this is suppose the process. In that case, the elementary matrix which is actually multiplying with A from the left hand side, that is suppose this is, I can write Ri plus Crj. This is the corresponding elementary row operation. So this is what it is. One can write E with the corresponding elementary row operation is that Rr. With row R you are multiplying C. This is what it is. Suppose this is the elementary. So this is what it is means that you have everything in the let's take a diagonal identity matrix. You just multiply that Rj Ri plus Rj. Suppose this is in the place of Ri dashed. Okay, this is what it is. I mean, Ri dashed, you are replacing Ri by Ri plus Crj. So that means in the ith row, its ijth position will be C. All other entry will be as it is. Identity matrix, okay, 1, 0, 0, 0, 0, 1, 0, 0, 0. So let's take ith row, that will be 0, 0, 0, 1 at the ith diagonal 1, and at the jth place, ijth entry, suppose this is on the right hand side, for example. That can be on left hand side also, that's not a big deal. 0, 0, 0, this here is something 0, 0, 0 is there, 0, 0, 1. So this is what it is. This C is actually on the I comma jth position, jth entry. All other entry will be diagonal, only the C position, then it will be ith row. Yes, this is correct. This is the ith row. And when you are interchanging, you have to interchange the row. Suppose you want to interchange I and jth row, you have to take the identity matrix, you have to change the I and j row. This is what it is. Okay. So now this matrices has very interesting, and another is that actually Ri dash is equals to what another is that another elementary operation is that, for example, you have Ri dash is equals to Rj, I and j are not equal. So that elementary operation, as I have said, we have to interchange the ith row and jth row. Okay. So jth row will be, I mean, I have to write in many terms. So this is basically we have to interchange ijth row. Okay. Just interchange ijth row in the E is equals to identity matrix with interchange of ith row and jth row. So note that here is C is also non-zero. Okay, C is non-zero. Here C can be zero. That's not a big deal. Here, I mean, this Ri plus Crj, there C can be zero, but in the when you are scalar multiplying, that has to be non-zero scalar multiplication. So all these row operations, what I just want to say is that all these matrix, they are invertible matrix. Okay. Elementary row operation means, as I have said, multiplication of all these matrix from the left hand side. So that means when you are, suppose you have a matrix A, after elementary row operation, you are getting row reduced form. That means this is equals to some invertible matrix P actually multiplying with A from the left hand side, which makes R. This is what it is I mean by elementary row operations, and this is what it is usually mean. So now this P will be invertible. Okay. So now the thing is that one can ask, what is that P? Suppose you are giving A and R, you are asked what is that P. So in that case, you have to do that. Okay, let's start the elementary row operations. Whenever you will get the some row reduced form, I mean, suppose you are giving here in this problem you are giving the matrix A, okay, and you are saying that you have to do some row reduction with A so that you will get B, and when you will get B, you have to stop that point because B is actually not row reduced form. Why B is not row reduced? Because this is the leading term of the second row, but the all other term in this case are non-zero. Okay, there is 2 4 1, they are non-zero. Okay, so that means this matrix is actually not, this is not row reduced, but that does not affect. Okay, you have multiplied with A some matrices from the left hand side, elementary matrices, so that you get the B. So you have to find that matrix P. Here it is asked that what is the matrix P such that, oh, okay, is there any, okay, let me reset. I mean, I think it's not clearly visible. Is it not clearly visible? Yeah, maybe my network is there is also, so that can also happen. Hmm, okay, now it's visible. Okay, that's okay. Thank you. Okay, so now here it is asked that what the matrix P one should multiply with A from the left hand side so that one will get the B. But as I have said, B is not completely row reduced. So let's write that matrix again because here we have written, I have written many things. So this is problem number 4. So here was the matrix. A is the matrix 1, 2, 3, 0, 1. You have to do the standard row reduction process. You don't need to do the anything. You'll get at the path of the row reduction process, you'll get the B. This is what usually give 0, 0, 0, 1, 0. This is what it is A giving. This is what giving. And we have to find what is the P one should multiply with A so that one will get the B. And the B is actually, this is what it is asked. What is the P? One should get B is equals to 1, 2, 3, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 2, 0, 0, 0, 0, 4, 1, 0, 0, 0, 1, 0. So this is the B it is asked. Okay. So let's do the, as I have said, let's do the standard row reduction process. Why I'm saying standard row reduction process? Because here is the leading term is 1, okay, of the first row, but all other terms as it is. So that means we have to do the make sure these entries are becomes 0. We have to do some row reduction so that this makes the row reduction, this is 0. So how one will get? So let's do this process. So what is the usual way? As I have said, if I want to make 2 3 1 0, what do we have to do? We have to do this process. R2 dash is equals to R2 minus 2R1, R3 dash is equals to R3 minus 3R1, and R4 dash is equals to R4 minus R1. And this process, each of them gives an elementary matrices, right? And here it is 1 2 3 4 5 5 by 5 matrices, right? 5 by 5 matrices. So each of them are elementary, correspondent elementary matrices. This will correspond to the elementary matrices 1 0 0 0 0. R2 I am replacing by minus 2, so minus 2 1 0 0 0. So this is the elementary matrices. This only this operation will denote the elementary matrix, this matrix, only this matrix. Similarly, this one will correspond to the elementary matrices. Okay, this one will correspond to the elementary matrix. What elementary matrix? This will correspond to 1 0 0 0 0. We have to do in third row, so we should not disturb anything in the second row. Only we'll go to the third row and multiplying R1 minus 3. So minus 3 0 1 0 0 0 0 0 0 0. Another, I think, sorry, this is 1 0 0 1. This is, and similarly this one, you know that fourth row you have to make sure that minus 1. So this one will be like 1 0 0 0 0 0 1 0 0 0 0 0 1 0 0. Fourth row you have to change, that is minus 1 0 0 1 0, and all other entries as it is. These are the elementary operations. Okay, this corresponding to this elementary operation. And after doing this row reduction, this all this, what I will get? First row will be as it is. These are the process. This is not actually, you have to mix. These are the actually. This is the actually the, I mean, in elementary row operation, what are the matrices coming, which has to multiply with the left hand side, so that we'll get the resultant matrix. This is what I want to mean. So, so it is 1 2 3 0 1, and we have to multiply row 1 with 2 and subtract it from the row 2. So that will be 0 0 0 1 it is, and 0 it is. Next is you have to multiply row 1 3 and subtract it from, that is 0 0 0 2 it is, 0 again. And okay, you have to subtract just only this one 1, and last is as it is. So note that this is what it is B given. This is what it is B given. So you have to ask that find to be. So you have to do the single row operations, not single. There is 3 row operations done, but so these are the actually standard process. What I am saying, that you have to multiply. I mean, basically, if you write this is as the matrix E1, this is as the matrix E2, this is the matrix E3. So what we have to, we are actually getting, all of them are square matrix, E1, E2, E3 with multiplying A gives B. Okay. So if you multiply E1, E2, E3, whatever you will get, that is same with the whatever. I'm just easy trick what I'm saying right now. Whenever you are doing these multiple operations at a single stage, in that case, because when you are doing or calculating something, you can't do all the steps step by step. You have to do some short process. You have to do some quick calculations. Okay, so you can't I mean detail everything. So all these steps are actually same with this one. Whenever, I mean, this elementary you are multiplying minus 2. I mean, first row change is this one. Second row change is minus 3 0 1 0 0. Fourth row change is minus 1 0 0 1 0 0 0 0 0 1. So this is same with this term. Basically, if you just say that this 3 operation is doing simultaneously in a single stage, this is what it is. And if you separately do, these are the all things. Okay. I mean, if you do this 3 operation R2 dash, R3 dash, R4 dash with the identity matrix in a single stage, you will get this matrix. And if you separately do this matrix, and if you multiply, you'll get the same thing, because this is standard thing, because this is upper triangle, so that will not create problem to multiplication. Okay. So this is the matrix basically. 1, this will be identity. Just first column will be 1, minus 2, minus 3, minus 1, 0. So let's see which option it is matching. 1 minus 2 minus 3 minus 1 0. This is the first and second both are third and fourth both are matching. But why third and fourth both are matching actually? Oh no, sorry. Minus 2 minus 3 minus 1. So second one is not matching. This is what it is matching. There is no 0, right? Yeah. So this is the answer. Yeah, this is the answer. Third one is the answer because fourth one there is 2 positive, not minus. Okay. I hope it is clear. And if there is any problem with visibility of my screen, you can also say that so that I can try to reshare or do something so that the visibility can get clear. Okay. Now let's do, yeah, this is an interesting problem. So this is the another problem. This is regarding vector space. But first I will discuss some vector space and subspace. Then I will go to this problem. So, but first let's read the problem. What it says: let V be a vector space over R, and let W and W to subset of V be subspace. Which of the following statement is or are always true? Okay, this is what it is asked. Which of the statement is or are always true? But what is vector space? I know all of you are know, but still, let V be a non-empty set and F be a field, then V is equipped with two operations. V is equipped with two operations. They are addition and scalar, as I have said in previous multiplication, which should satisfy some condition, which satisfies some conditions there with respect to addition. With respect to addition, V is scalar multiplication means you have field and you have V, F cross V to V. That means you have to take scalar means elements from the field. This is what it might mean by scalar. And vector is like this. V is a vector, something like CV to, suppose C and V are two elements. So whatever that this CV should be element from here. This is what it is by what I mean. Okay. So with respect to addition, V is just usual addition and scalar multiplication. Scalar multiplication means multiplication by field entries. And addition is addition between two elements in the set V. V is an abelian group or commutative group, same thing. Commutative group with respect to addition only. Okay. Second is that scalar multiplication is closed. Second is that one can say that scalar multiplication is closed. Multiplication is closed. Closed means, as I have said, C is coming from F, V is coming from V, C dot V, that has to be element from V. It's closed. Second is that associativity, that C1, C2, two entry from field, and V is an element from field. Then C1 dot C2V is equals to C1 C2V, or this is what it is, means associativity. This is what it is, and you can interchange C1, C2 because field they are commutative. So this is called associativity, CRTVT. Okay. Third is that one there exists an entry. One is the unit element in the field, unit in field F. These are there, which I will not go discuss. 1 dot V has to be V for all V in V. Okay. This is the scalar multiple I mean. When I write dot, that means scalar multiple. When I write addition, that is the addition on V. And the fourth is that it has to be distributive from the field and V from the capital V. Then C1 plus C2 dot V is equals to C1 V. This is dot plus C2 dot V. And another distributive property is that C from V, C from F, and V1 and V2 from V. Then C dot V1 plus V2, that is equals to C dot V1 plus C dot V2. This is what has to be. Okay, these are the property vector space. I know everyone you know, but okay. Now the other thing is that subspace. Now our non-empty subspace. A non-empty subset. So basically starting with the let V be a vector space over the field F. Let V be a vector space over field F. Okay. F and B, what it is doing that we have seen already. And W, B are non-empty subset. Subset of V. Okay. Then when we say what we mean by subspace, then W is said to be subspace of V. That has to be non-empty first of all. This is non-empty. Subspace of V if W itself is a subspace. W itself is a subspace over F. But this is equivalent. This fact is equivalent. Equivalent one can say. There is an interesting fact that a non-empty subset, not fact, that is a theorem basically. This is also discussed in class. Non-empty subset W of V is said to be subspace if for any C belongs to the field V1 and V2, two entry from V, C V1 plus V2 belongs to the set W. This is not V, this is W. This will do every property, I mean these two property with the inherited property from V. Whenever W is a subset of V, there should be some property which is inherited from V. And now, if we take V1 and V2, I mean if we have this property, then it's okay. A non-reducible is said to be subspace if for any then this. Okay, then okay. If this holds for any C belongs to F, V1, V2 belongs to W, then C V1 plus V2 is in W again. Then that will be subspace. I will not prove that one, but that is what it is the best tool one can use to check a subspace or not. But the first thing which I should advise to everyone, that when you have a set subspace and you are asked to check whether this is a vector subspace or not, first thing you should check whether 0 is there or not. 0 will be there. How 0 will be there? You just choose V2 is equals to 0 and V1 is equals to 0. Still the 0 will be in, still C V1 plus C V2, that will be 0. Sorry, no. So this is the mistake I am making. C V1 plus V2 is in W, whether 0 is there or not. This is first place. So let's take V. Let's take any arbitrary element V. Any arbitrary element V, that is V1. And V2 both are same. Let's take V is an element in W, and let's take V1 equals to V and V2 is equals to V. And C is equals to -1. Then what it will happen? Minus V1 plus V2. This is equals to minus V plus V. That is 0. That has to be in W. Okay, for any V. And we have taken that W is actually non-empty. So that means there will always exist an element V. Okay. Whenever W is non-empty set, if this property holds, because this is in the standing assumption that if we want to get a subspace, that has to be non-empty. Whenever non-empty, there should exist an element V. And whenever you have V, let's choose V1 is V and V2 is again V. And field has the minus, C can be taken -1. So 0 will be there. This is something. So that's why it's always advised to check first whether 0 is there or not. Okay. With these two definitions, with all these discussions, let's get back to the problem. What is the main problem? That V be a vector space over R, W and W2 subspace. Which of the following statement is or are always true? First of all, W1 intersection W2 is subspace or not. This is what it is. So let's check. Before that, I should not. Yeah. So let's take W1 W2 is a set. We have to check that is subspace or not. So let's take V1 and V2. This is in again W1 intersection W2, and C is an element. C is the scalar in the field F. Okay. So now whenever C scalar field F, so as V1 and V2 both are in W and W2 intersection of, so that implies V1 and V2 both are in W1 and again both are in W2 and C belongs to F. But it is given that W and W2 are subspace and V1 V2 in W and C belongs to F, so that means C V1 plus V2 that is in W1 because W1 is a subspace, and again similarly as W2 is subspace, C V1 plus V2 that is again in W2 because W2 is subspace. Now this term is in both W and W2, that implies C V1 plus V2 that is in W1 intersection W2. Okay, so that says W1 intersection W2 is again a subspace. So this is correct. 0 is there. Actually 0 is both in W and W2, so that's because they are subspace, so that's why they will be there. So their intersection it will also be there. This is very easy. Okay, now let's go to the second one. W1 plus W2 is not necessarily a subspace of V. So whether this is true or false, so if we can prove that W1 plus W2 is actually a subspace, then this will be false because this is said that W1 plus W2 is not necessarily a subspace, but we will show that W1 W2 actually subspace. Let W1 and W2 are subspace of V. Then what I mean by W1 plus W2, that is equals to just W1 plus W2. This is the vector space. Here is V, there is an addition, so this is the addition. And where W1 is coming from capital W1 and W2 is coming from capital W2. This is what it is I mean by W1 plus W2 as a set. Okay. Now what we have to prove that this is a vector space or not. Similarly, let's take two element W1 plus W2. Another, this is one element. Another element is W1 dashed plus W2 dashed. This is another element both coming from W1 plus W2, and C is an scalar in F. So what we have to prove? C of W1 plus W2, this plus W1 dashed plus W2 dashed. This is whether question is whether this is in W1 plus W2 or not. This is what it is, the main question. This is what we have to check. So but let's see whether this is there or not. Then this is equals to C W1 plus W1 dashed. Okay, because distributive property is here, and C W2 plus W2 dash because distributive property is here. Now as W1 is subspace, W1 and W1 dash both are in W1 because this is what it is I mean sum of two element. Okay, so this is in W1 and this is in W2. I hope this is clear. So that means this is in W1 plus W2. So that means W1 plus W2 is subspace, is again subspace of V. I hope this is clear. So that means the second option is actually false. The other two options I am checking. Just 1 second. Okay, so second option is false. Now third one is that if W1 intersection W2 is 0, then W1 union W2 is subspace or not. But before that, before whether this is true or not, here I am doing, this is a theorem actually. W1 and W2 to do subspace of V. W1 union W2 is subspace or not. That is subspace under some condition. So this is what is theorem one can say. So this is theorem. W1 and W2 are subspace of V. Then W1 union W2 is again a subspace of V, is again subspace of V if and only if W1 subset of W2 or W2 subset of W1. W1 and W2 both are non-empty because they are subspace. Subspace has to be non-empty. So this is the theorem. What I have said, that W1 and W2 two subspace of V. Their union, interesting that what we have seen, intersection of two subspace is again subspace, right? That is the first option. Sum of two subspace is again subspace. That was the second option we have checked. But here is the question, when the union is again subspace or not. This is the question. That is subspace only a specific situation, whether when W1 is subset of W2 or W2 is subspace of W1. So there is three type of operation one can do with the set, and another operation is actually the subtraction. But subtraction is not doing here, because when you subtract to one set from another set, both case zero is there. W and W2 is subspace, right? I mean, okay, let me tell it from the beginning. Whenever you have two subset or subspace, there is four type of operation one can do. One is the addition, one is subtraction, another is intersection, another is union. Subtraction means subtraction. You have to subtract W2 element from the W1 element. Okay, like set subtraction. It is suppose W1, it is W2. So W1 minus W2 means this is the portion. This is the sided portion. This is what I mean by W1 minus W2. But this is not a subspace. Why this is not a subspace? Because you have 0 in both cases. W1 and W2 both 0. So whenever you will subtract W2 from W1, 0 will be deleted. So this set will not have 0 again. If this set does not have 0, so this can't be subspace. So this is not a subspace. So three case is clear. Addition, union, addition, intersection, and subtraction. This is clear whenever it is subspace or not. Now it's come only the union. Union will be if and only if this holds. So let's see how it will hold. If W1 subset of W2 or W2 is subset of W1, then W1 union W2 is actually, in this case it is equals to W2, and in this case it is W1 union W2 is equals to W1. So that says, because W1 and W2 both are subspace, that says W1 union W2 is again a subspace, because W1 and W2 they are subspace itself. So that means if this happens, then W1 W2 subspace. That's clear. Now the other part, if W1 and union W2, now conversely, if W1 union W2 is a subspace of V, then we have to prove that either W1 is subset of W2 and W2 is subset of, or W2 is subset of W1. But if W1 union W2 is a subspace of V, but neither W1 is a subset of W2 and W2 is not a subset of W1. So that means W1 is not a subset of W2 and W2 is not a subset of W1. Then what I will prove that 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 will create a contradiction. Then we are done, because then one has to be failed. Either W1 union W2 is not subspace, or any one of them has to be failed. And where we have considered that W1 union W2 is subspace, that is the standing assumption. But assume that W1 is not a subset of W2 and W2 is not a subset of W1. If we assume these two, then that will create a contradiction. So let's see what is the contradiction. So let W1 is coming from capital W1 and W2 that's coming from the capital W2. So note that W1 is actually subset of W1 union W2. This is W2 is again subset of W1 union W2. So that means W1 plus W2, or one can say W1 union W2, that's in both W1 union W2. So that says the vector space operation, that W1 minus or plus, that does not affect, that will also be in W1 union W2. W1 union W2. So the now thing is that, so now as this element is in W1 union W2, now what is the set theory says? Suppose you have AB and X an element in A. That means X is either in A or X is in B. This is what it is means. This is what it is set theory means. So that is imply that either W1 plus W2 is in W1 or W1 plus W2 is in W2. So if this happens, we know W1 is in capital W1. So that implies W2 is in capital W1, but that is that contradicts to the fact that 2W2 is not a subset of W1, because that will create contradiction, because W2 is an element, and this is true for every two. As no, so better to write this one. Okay, just a minute. And this holds for every W1 W2 is in. So that implies that every W2 is in W1. That implies W2 is a subset of W1. This is a contradiction. And similarly here what will give W1 belongs to W2. That implies W1, and this is true for any W1. You can start with any W1 W2. Okay, W1 is subset of W2. That is a contradiction. Okay, so that means we have to I mean, this contradicts the fact that W2 is subset of W1. We have assumed that W2 is not subset of W1, and here we have assumed that W1 is not subset of W2. Okay, W1 is not subset of W2, but this is what we are getting. So that means there is a contradiction. So that means at least we have to, if we assume this is subspace, then at least one of them has to be subset. So that is, if W1 union W2 is a subspace of V, then either W1 is subset of W2 or W2 is subset of W1. So now what this is the theorem proved. Now the thing is that let's get back to the main question. The main question is that we have checked with these two options, first two options, whether W1 intersection W2 is subspace or not, W1 plus W2 is subspace or not. Now the fourth option says that this is true. This is what I have proved right now. The W1 union W2 is a subspace of B if and only if W1 is subset of W2, W2 is subset of W1. Now this is if and only if. Now let's look at the third statement. What it says: if W1 intersection W2 is 0, then W1 union W2 is a subspace or not. That's not necessary. Unless W1 is subset of W2 and W2 is subset of W1, W1 union W2 will not be a subspace. Even W1 intersection W2 is 0, that does not guarantee that W1 will be a subset of W2 or W2 is a subset of W2. So that means this is false. Okay. So what we get, that W1 intersection W2 is a subspace always. W1 plus W2 is a subspace. W1 minus W2 is not a subspace. W1 union W2 will be a subspace if and only if one of them are subset of other. This is what we learned from this question. If there is any doubt or any repetition is required, you can ask. I'll try to repeat. And if there is any problem in the visibility, still you can ask or you can write. I'll try to sort that problem. Yes. Yeah, just a minute. Is it visible? Okay. No, sorry. You are saying that, no, what we have to do, okay, what we have to do, we have a set. We have a set like, just a minute. Suppose you have a set A, okay, you are taking two element x, y belongs to it, and suppose A is actually A1 intersection A2. So what it mean? It mean x and y both in A1 and x and y both in A2, right? No, actually there is no problem. Oh, now if you want to prove that A is a subspace, what we have to do for let's take two element xy belongs to A and C element from the field. What you have to show, just you have to show that this is your target. Target is that forget about that A is actually A1 intersection or A2 not. A is a set. You have to, if you want to prove that A is a subspace, what you have to do? Let's take two element x and y from A and scalar from C from F, and you have to prove that Cx plus y is again in A. This is what you have to prove. This is your target. Okay. Now here A is actually W1 intersection W2. Now we should not take other terms. Why I am saying we should not take other terms? Your target terms is fixed. X, Y, C, they are arbitrarily taken, but right now they are fixed. Arbitrarily taken, but right now they are fixed. So you have to choose you have to just show, this is your target. Cx plus y is in A. So now x and y is in W1 intersection W2. That will now, if I want to prove that, we have to use some properties of W1 and W2 which is already exist. They are subspace. So now x and y both are in W1 and x and y both are in W2. These are the result of assumption that x comma y is in A. We are getting out of that. We want to get sure that Cx plus y is in A. This is what I want to show, right? Now as x and y is in W1 and x and y is in W2 and C is in field, we know that W1 is a subspace. So now as W1 is subspace, as I have mentioned, that Cx plus y, that has to be in W1 because this is what is its property. And again Cx plus y, that has to be in W2 because that is the property of W2. Now these two will make sure that Cx plus y is in W1 intersection W2. Now, now do you have any doubt right now that you should choose other entries? Because what I want to say is that we are not choosing other entry. We have choose two entry x and y from A and a scalar C or element from the field you have already chose, and you want to target is that your target is this Cx plus y is in A. This is your target. Now if you want to achieve that target, how to proceed? This is the steps. You have to use the properties of W1 and W2. Is it clear or should I try to explain some different angle? No, no, yeah, that's true. That's true. Yeah, right. You are correct, correct. You're correct. But whenever you are taking W1 intersection W2, that set, whatever the entry in that set, those entries are both in W1 and W2. Do you agree that? That can be zero only. That can be zero. That can be only zero entry. But that doesn't matter. But okay, let me tell you what I want to say here. Suppose you have W1. This is W1. You have W2. This is W2. You are taking intersection portion, right? Your target is that if you take x and y from this set and see some element from here, you want to prove that Cx plus y is in here, right? So here can be element. Here also can be element. Maybe you are saying that element which is not in the intersection portion, right? But we don't care about the element on that portion. That W1, V1, V2, those all are from in this section. If there is element, we are not care about those elements. We are not considering those elements, right? We have to say that if I take an element from here, the intersection portion for that two element, whether this holds or not. That can be, this intersection can be empty as well. I mean, not empty, zero. Empty it is not possible, zero, because zero both in W1 and W2. Is it clear? Because this is very fundamental thing. I mean, initial thing. You should be clear. Even it is not clear to you, you can say, I will try to explain again. Not a problem. Is it clear? Yeah. Okay. This is fundamental. If you have any problem, you'll face in the problem in the next things. So if you have fundamental clears, then okay. This is another problem. Let's take this one. So what it says, let P4 be the vector space of polynomials of degree less than or equals to 4 over R are real number with respect to the standard vector addition and standard scalar multiplication. Vector addition means, standard vector addition means just you are taking two polynomial. Suppose a0 plus a1x plus all the way a4x to the power 4. Another is b0 plus b1x b4x to the power 4. So addition is actually a0 plus b0. This is standard addition mean b1x plus all the way a4 plus b4 whole to the power x. So this is standard addition. And scalar multiplication means, let's take scalar multiplication means just multiplication with the, this is the, suppose C is coming from F, the field, CA0 plus CA1. So here it is C is real number basically, field means real number. CA1 x plus all the way CA4 x to the power 4. This is standard addition and multiplication means. W be a subspace of P4 consisting of elements Px, then Px can take the form. So basically what it is saying, what is the question says, this is the question says, P4 is the space of all polynomials, real valued polynomials of degree less than equals to 4. Less than equals to 4. Okay, this is P4 means. And W, here is what is mean by W. W is equals to saying all those entry Px is equals to a0 x to the power 4 plus a1 x cube plus a2 x square plus a3 x plus a4 such that this condition, this four condition, any by one. If we have this condition like a not greater than equals to 0, let's consider this is W1. I mean, with all this terminology, these are the terminology. I mean, this with this condition W1. If the condition is A2 is equals to A3, let's consider that is W3. If the condition is only A4 is equals to A1 plus alpha square A2 for some alpha belongs to real number, then called it, this is W2, call it W3. And if the condition is that A4 is rational, call it W4. So basically what I want to say is that this with this condition, I have to write 4 times, so I am not writing 4 times. This is what I mean. So suppose you are closing here, W1 is equals to this, W2 is equals to this, same with this, something like that. This is what I want to mean. Okay, so this with first condition we will say that W1, and this with second condition, this with first condition will say W1, this with second condition will say W2, this with third condition will say W3, and fourth condition W4. So first condition is says that A not greater than equals to 0, second condition says that A2 equals to A3, third condition, they are not simultaneously will have. Basically what I want to say is W1 is equals to just Px is equals to A naught x to the power 4 plus a1 x cube plus all the way a4 such that a not greater than equals to 0. This is W1. W2 is equals to Px is equals to a naught x to the power 4 plus a1 x cube plus all the way a4 such that a2 equals to a3. This is W2. Similarly W3 and W4, this will only change. A4 is equals to a1 plus alpha square a3, and W4 will be same with that A4 is rational. So now the question is, which of them are subspace? This is what it is the question mean. So now, as I have said, it will be subspace if it satisfies these two property, that for any two elements. So let's write P and Q, two element in W1 and Wi, and C is in the field. Wi means for any I equals to 1 to 4, we need to show, we need to check, see, this is real number, need to check that whether Cp plus Q, this is again in Wi or not. This is what I have to check. Okay. So now if you are taking that collection of all 4-degree polynomials for which this A naught is actually positive, greater than equals to 0, whether that is a subspace or not, the answer is no. Why? Because if you take minus 1, let A naught x to the power 4 plus, So W1, I'm checking W1 plus A1x cube plus A2x square plus A1x plus A4. This is in W1 and A naught is greater than equals to 0. One can take 2, 3, 0, some 0 also one can take. Okay. This is not a subspace. Okay. One can take A naught is 1 also, right? For example, you can take A naught 1. Minus 1 as a scalar is in the field real number. Now, if you multiply minus 1 with this P, what you'll get? Minus A naught x to the power 4 minus A1 x cube minus A2 x square minus A1x minus A4. Now, initially we have taken A naught is actually positive. For example, let's take A naught is equals to 1. So right now it is becomes minus 1. So now, right now it is a new form A naught dashed x to the power 4 plus A1 dashed x cube plus A2 dashed x square plus A3 dashed x plus A4 dashed, and where A naught dashed is equals to minus A naught and all other entries, something like similar. But A naught, if I take positive real number, then minus A naught is actually negative, right? So that means this is negative, but that contradicts because that implies that minus 1 times P that does not belongs to W1. Okay, so that says that W1 is not a subspace. Similarly, we have to check the other. So, but this will be subspace. Why I'm saying W2 is equals to, as I have said, I will not write. So let's take, I will not write again. Let's take P is equals to A4 x, sorry, A naught x 4 plus A1 x cube plus A2 x square plus A1, sorry, A naught A3 3 4x plus A5. I think up to 5 symbol was there. Yeah, it has to be 5 symbol. No, not 1 2. Here it will be 2. Here it will be 3 A4. And here it is giving there, suppose A2 equals to A3. This is what it is, the condition. A2 equals to A3. A2 equals to A3, and another is that Q, which is equals to something like that, A naught dashed x4, A1 dashed x3, A2 dashed x square, not x3 actually, x cube, A3 dashed x plus A4 dashed, and here is also A2 dashed is equals to A3. Now let's take, this is arbitrary element I am taking, these two are element in W2, and let's take C is an polynomial element in the field. Then CP plus Q, this is what it will be. This will be C A naught plus A naught dashed x4 plus C A1 plus A1 dashed x cube plus C A2 plus A2 dashed x square plus C A3 plus A3 dashed x plus C A4 plus A4 dashed. But I have to check whether this is in W2 or not. This is what I want to check. So for that, what is the condition we need? That this coefficient is actually same. This is same with this or not. Coefficient of, no. A2 is equals to A3. Sorry. So whether this term is same with this term or not. This is what I have to check. Okay. Basically, coefficient of x square and coefficient of x, they are same. This is the standing condition to be an element in W2. Okay. That A2 equals to A3. But this is same. But note that CA2 plus A2 dash is equals to CA3 plus A3 dashed, because A2 is equals to A3, this is giving, A2 dash is equals to A3, so this is giving. So that implies that CP plus Q is in W. Okay. So W2. So this way W2 is will be, this is a correct option, then Px can take the form. This is not correct option. A naught is not the correct option. This is correct option, because this is, if you take A naught is greater than equals to 0, then it is not making vector subspace. Wn is not a subspace. W2 is subspace. And similarly, W4 will be subspace. This is check. I will not write. This is check. Similarly, I'll just discuss W4 only. This will not be. Here it is written that A4 has to be rational. So that means W4 was that collection of all those polynomials. P is equals to A naught x to the power 4 plus A1x plus A2x square plus A3x plus A4, such that A4 is rational. This is what is the standing assumption. This is W. W4 is collection of all those entries. So let's take P is such like that. And let's take square root. Let's take A4 is equals to 1. For example, square root is in the field F, which is actually real number. Now multiply square root with the P, which is P is in W. What you'll get? You'll get square root of 2 a naught x to the power 4 square root of 2 a1 x plus square root of 2 a2 x square plus square root of 2 a3 x plus square root of 2 a4. I have taken 1. Okay, but a4 I'll write. So now if we take a4 is rational number and if you take this is irrational number, then this product is actually is not rational. So that implies root 2p is not in W4. That implies W4 is not a subspace. Okay, so R1 you can check, that will be subspace. So this is not a subspace. So this will solve the full problem. So first one, a not greater than equals to 0, that is not going to help. That is not a subspace. A2 equals to A3, that is a subspace. A4 is equals to A1 plus alpha square A2, that will be again a subspace, because similarly you can check like A2 equals to A3. A4 rational number, then that is not subspace. Okay, so this is all for this problem. Now I'll do one more problem and I hope that will be the last problem for today's. Till that, if you have any problem you can ask, and even in these questions if you have any doubt you can ask, or if it is clear then it's okay. Even simpler doubt you can ask, because as I have said, it's better to clear your doubt instead of being in doubt. I mean, to spend a whole semester in the same wrong knowledge. It's better to clear that doubt here. Okay, so I'll do one more problem as I have said. That this is done. This is also done. Yeah, this is a problem. So this is another problem that is also regarding subspace. Let V equals to R3, that is the vector space, that's tuple of 3 entries. Okay, which of the following subsets of V is a subspace or not? So as I have said, check to check a subspace, we have to first check whether 0 is there or not. First case, set of all vectors of the form xyz where x plus y plus z equals to 1. Whether 0 is there, 0 is not there. Okay, so this is not a subspace. As 0 comma 0, this is the 0 of V, right? This is not in W. Let's assume that W is actually the set. These are the set. This is the set. W is collection of all x, y, z, for which x plus y plus z equals to 1. W2 is collection of all vectors x, y, z, for which x, y, z greater than equals to 0. Which of the following subsets of V is subspace? Okay, and W3 is actually the subset set of all vectors of the form xyz for which x plus y plus z equals to 0, and set of all vectors of the form xyz such that this holds. Okay, so first one is not there, so that's why I can say that this is not a subspace. That's clear, very clear. Okay, as 0 is not there, sorry, 0 is there, 0 is not there, because 0 0 0 sum is not giving 1, so that's why this is not a subspace. Okay, also other way you can check. For example, if you have two entry, other way, I mean the detailed way, suppose you have two element x1 x2 x1 y1 x y1 z1, this is one entry, and x2 y2 z2, this is general entry I am taking in wi, one can say w, this is suppose w1 w2 w3, something like that. C is in field. Now if you take C this is suppose the first entry. So first entry, so C of this is the first entry x1, y1, z1 plus x2, y2, z2. As they are in the first one, the w1, for example. So w1, as I have said, x1, y1, z1 is in w1 and x2, y2, z2. This is in w1. So here w1 is equals to all those x, y, z is in v, which is actually r3, such that x plus y plus z is equals to 1. So this is what we have. So that means this gives x1 plus y1 plus z1 is equals to 1, x2 plus y2 plus z2 is equals to 1. This is what it is in the standing assumption, because they are in the their entries in this set. Okay, but as I have said, C belongs to, let's take F, and C x1 y1 z1 plus x2 y2 z2, that is equals to cx1 plus cx1 cx1 plus x2 cy1 plus y2 cz1 plus z2. Now question is whether this is in w1 or not. Okay, let's check. Cx1 plus x2 plus, this is the first entry, and cy1 plus y2, this is the second entry, cz1 plus z2, this is the third entry. So this will be like c x1 plus y1 plus z plus x2 plus y2 plus z2. As I have said, x1 y1 z1 is w1 and x2 y2 z is w1 again, so that's why their sum is always 1. So this will give c plus 1. So this will be 1 unless this is not equals to 1, unless c is equals to 0, but one can choose c is not equals to 0, right? So that means this is not equals to 1. This is not equals to 1 always. Okay, so that gives that w1 is not a subspace. Similarly, so that makes, and that as I have said, directly you can say 0 is not there, that's what is not subspace. That's all. Second is that set of all vectors of the form xyz where xyz are positive, whether that is not. That is again not, because if you multiply by a minus 1, those terms will be minus, and that is not there. So let's write w2, which is equals to all xyz in R3, which is actually V, such that xyz greater than equals to 0. So now let's take minus 1. Now let's take xyz is an element in w2 and c is equals to minus 1. Multiply c x y z. At least if this is a vector space, w2 is a subspace, this entry has to be in w2. But here I will make sure that this is not in w2. Minus x, minus y, minus z. Okay, and let's take x is not equals to 0. So that means here implies minus x is actually negative, because x is not equals to 0, but x is positive. Okay, x, y, z can be 0 but also positive. Positive also can be, but here I am taking that x is not positive. Sorry, not 0 but positive. So that's why it's making minus. So that's why that is not in w2. So that says w2 is not a subspace. If there is any doubt, they are very easy, but even there is any doubt, it's better to clear. Okay, so if you have any doubt, you can ask, not a problem. So this is not a subspace. Set of all vectors of the from xyz such that xyz equals to 0, that is again a subspace. W3 is equals to all xyz in V, which is actually R3, such that x plus y plus z equals to 0. So similarly, I will take x1, y1, z1 and x2, y2, z2. These are two entry in W3 and C element in F. So let's write cx1, comma y1, z1 plus x2, y2, z2. Here all are arbitrary term. Okay. So this will be, I am writing directly cx1, x2, cy1 plus y2, cz1 plus z2. Now whether this is in W3 or not, this is the question, whether W3 or not. For that, what I will do, I'll just take their sum, whether that becomes 0 or not. Okay, so let's take sum of them. This is equals to c x1 plus y1 plus z1 plus x2 plus y2 plus z2. Note that as xy these are entry here, so their sum is automatically 0 because this is the standing assumption being an element in W3. So that makes this is 0, whether C is 0 or not, that does not care. Okay, so this is 0, so that implies W3 is a subspace. Okay, D is obviously not, that I can assure you. Okay, but let's write D for a quick example. D, that is equals to W4 is equals to all those x, y, z belongs to R3, which is actually the vector space, such that the question condition was x square plus y square minus z square is equals to 0. Let me check if this is correct or not. Yeah, this is what it is. So whether this is hold or not. So you can easily take an example where it is not happens. Scalar multiple will hold. That's true. Without scalar multiple, you have to do the addition. Okay, let's take 2 addition. I think one can do 1 square root. 1 square root. This is the entry in W4 as 1 plus 1 minus 2, that is equals to 0. Another entry is that 2, 0, 2. This is there. This is also in there, right? As 2 square plus 0 minus 2 square is equals to 0, right? More easily one can take. I don't need to, that is toughest one. 0, 1, 1. This is there as 0 plus 1 minus 1 is there. Okay, now let's add these two terms, or it will be 2 comma 1 comma 3, right? So whether but 2 square plus 1 square minus 3 square, that is what it is. 4 plus 1 5 minus 9, that is equals to minus 4, that's not equals to 0. So that says that addition is not happening. So how it can be vector space? That says W4 is not a subspace of V. Okay, so till now, is there any doubt? You can ask now. I am waiting for a few minutes, 1 to 2 minutes. And I must say that from now onwards till the end of this course, every Saturday from 6 p.m. to 8 p.m. these tutorial sessions will hold. You can ask any problem of this course, even any linear algebra problem you can ask. I'll try to answer that. You can also mail me to this email ID. If you have any doubt, you can mail me this one, smail.iitm.ac.in. I'm also writing in the chat. If you want, you can. If you have any doubt, you can ask to me in this mail ID, which I'll try to address in the next tutorial sessions. Or even you can ask me in tutorial session itself, in the tutorial sessions, any problem if you have. Okay, and if there is any change in the schedule of this course, then I will inform, and that will be mostly on the Friday or in the Sunday. That's shift, and that possibly 1 or 2, not more than in this whole session. In whole course, the change will be only in the 1 or 2 class, possibly, but maybe not also. Okay. Okay, so if you don't have any problem, we'll be stopping here. So I'll wait 1 more minutes. You can ask if you have any problem, otherwise you can leave. You can ask me any easy problem. Okay.